Hello and welcome back to Data Science CastNet. In this video I thought we'd do something fun and take a look at the concept of diffusion models for language modeling. And so we'll talk a little bit about the theory and how they differ from traditional autoregressive language models, but I'll also show you how we can play around with the concepts using an existing model, specifically the ModernBERT series. We'll adapt it into a quote-unquote diffusion LLM. We'll sample from that and get a bit of an intuition for how the process looks, and we'll also start to see some of the flaws that exist in the sort of naive vanilla approach to diffusion modeling of language, and then we'll brainstorm some ways to address those and explore those, and I'll suggest lots of experiments that you could do if you were interested in digging into this topic. And by the end of it, we'll have a model that we can sample from, but we'll also have plenty of ideas for how we could improve that. So this is something that I've just started experimenting with, but I thought I'd share this video and then I'll continue experimenting my track, but I also want to get other people involved, trying out different ideas and sharing them together in community. Okay, so let's start with an actual paper. This is Large Language Diffusion Models, LADA. And so they talk about how autoregressive models is kind of the default for modeling language. This was in February of this year. Since this paper, we've seen a few other players show off variants of diffusion language models, notably Google have a Gemini diffusion, and several other like sort of closed source players. But LADA was the first, I'd say, like, broadly competitive model to hit the scene that kind of proved out at least 8 billion parameter scale that this idea could potentially work. And so the key part of this here, and we'll look at this ourselves as well, is that instead of predicting the next token in a sequence, you have a sequence of tokens. Some of those get masked, and the amount of masking is variable between like nearly 0% or nearly 100%, and then you're going to predict the masked tokens. And then at inference time, you can feed in a prompt. So this blue portion corresponds to like the user's question, and then a bunch of mask tokens, and we're going to try and predict what those mask tokens could be and like gradually unmask them, right? Very much like in diffusion images. You would take an image, you'd add a bunch of noise to it, and then at inference time you would have a model that's learned to predict the image given a noisy version of the image. You'd start from a completely noisy image and you'd gradually like refine it into something that actually looks like an image. And in between there's a bit of adapting to take something that's learned to just predict uniformly scattered masks and switch it to being used to seeing an unmasked prompt and then variable amount of masking on the response. Okay, so that's the sort of core idea. It really is pretty much that simple. But as we start to explore it, we'll come back and look at this paper again to see like, oh, maybe is it that simple? Are there nuances? Are there things we need to address? But before we dive into code, maybe let's just dwell a little bit on the differences between these two approaches. Right, so I have here on the left a kind of very cartoonish representation of an autoregressive language model, right? So we have some sequence of tokens, the cat sat on the, and during training, we're going to feed this whole sequence through, and we're going to use so-called causal attention. And what that means is that tokens can only attend to tokens that come before them in the sequence. So for example, when you're looking at the word cat and it's passing through our big network, it can't pull in information from the future of the sequence. It can only pull in information from the preceding words, in this case just the, right? So that's not a very rich representation. But when you get to sat, it's like, okay, we're looking at the word sat in the context of cat and the, right? So you can imagine the model learning to like enrich this as like not just sat as in general sitting, but this is specifically feline sitting, right? And so on and so forth. And then as these pass through the model, once you get out the other side, for every single position, right, position 1, 2, 3, 4, 5, we're going to predict the next word in the sequence from that position. So for the first token in this input sequence, we want to predict cat, right? So we want to get right at the end of the network some representation that's then rich enough for us to predict, oh, the next word is probably cat. And we're actually going to predict a distribution, right? So we say maybe cat is the most likely, but could just as easily be the bird or the plane or the person. And so we would have some distribution of probabilities, but the correct label in this case would be cat. And so a few things worth noting here. One is during training, we're getting signal from every token, right? Because this cat here is compared, maybe we predicted, the man, right? And so we can have some sort of loss there. And then at the next position, we're saying, okay, the cat what? The cat walked, the cat meowed, the cat, etc. We get the correct label sat. And so we updating for every single token position, we're getting a correct label. And so we're getting a very rich training signal. Okay, so that's the autoregressive training, and we're doing this predicting the next token. And at inference, if we wanted to ask a question like where do cats sit, we could feed in the sequence user, where do cats sit, assistant colon, and then just one word at a time we'd say cats often sit on mats, right? We do one token at a time, and each time we'd feed the whole sequence through and get predictions, and then we'd throw away all of these predictions because we already know those, but we just look at the next, okay, this is the next actual like new token in the sequence. Okay, so let's contrast that with a masked language model, right? And this could be the diffusion model from LADA, but this could also be a much more like old school and common model like BERT. And so BERT and all of the BERT, DeBerta, Roberta, ModernBERT lineage, they're all trained during pre-training on this kind of mask prediction task. So some percentage of the input tokens are masked, right? You can see here we've got an input token. We feed the whole sequence through, and then unlike the autoregressive case where we had a label for every token, here we only have labels for the masked tokens, right? So everywhere where there's a mask on the input, the cat mask on the, and so on the rest of the sequence, we now need to predict what actually fills in this gap. And so in this case, the correct label would be sat, and we would again have a distribution of predicted tokens. We predict the cat sat, the cat threw up, the cat played, etc., right? And so we'd have our predictions for what would fill in that gap. And so you'll see the training signal is a little bit more sparse, right? Because now we only have typically something like a 20% masking ratio. ModernBERT, huge or large, trained on maybe like 30 or 40% masking ratio, and there's nuances there. But so you're getting less training signal per sample, right? You're not learning from every single token, or at least you're not getting a fine-grained loss from every token. You're only getting it from the places where there's a masked token, but still pretty useful. And then historically, the way these models have been used is then you then throw away that mask prediction part of it, and you just use the fact that this is hopefully learned useful representations of each of these words, because they're, unlike the vanilla case, every token here, including the mask token, is attending to every other token. And so there's no causal masking in the attention layers. Every token can pull in information from before and after it in the sequence, and that hopefully, as it learns to do a good job predicting the mask tokens, it's also learning useful representations of everything else. And so typically these models were then fine-tuned on downstream tasks like classification or retrieval or whatever. Okay, but hypothetically, if we had a masked diffusion model, sorry, a masked language model that predicts for these masks, and it had been trained seeing different amounts of mask tokens, right? Something like the LADA training where we have a random mask ratio, then we would be able to sample from that by feeding in a sequence that includes some text, user, where do cats sit, assistant colon, and then we could just feed in a bunch of masks, right? And so this whole sequence is going to go through in parallel. For every place where there's a mask prediction, a mask token, we're going to get a prediction of what actual real token should fit there. And so hypothetically, we could then get a full answer all in one single go, right? So rather than having to go one forward pass for every single position, one at a time like that, we could go for the whole shebang all at once and get our prediction. Unfortunately, as we'll see, that's probably not an amazing prediction, but we could do some tricks inspired from the multi-step sort of progressive refinement of diffusion models. Maybe we could only unmask a few tokens at a time, right? So maybe we could switch in to and on, right, as like maybe probable tokens. And then we feed that whole sequence through again, and this time being able to see that that word's to and that word's on, maybe this word is like, right, and this is mats, because we're talking about cats and sitting. And then the next time you feed that through, well, it's obvious that this is sit, and maybe this is cats. And so this kind of like progressive unmasking is a way that we can sample from these models more richly, and also a way that we can choose how much compute we want to spend, right? So one big kind of highlight feature, one reason people are excited about quote-unquote diffusion for text is that you don't necessarily have this one-to-one correspondence of one pass through the model for every single token we want to generate. You could instead do a pass through the model where you generate, tens, hundreds of tokens. So there's a potential for huge speedups there. And indeed, that's what the LADA paper and many other diffusion-like LLM papers do, is they predict for the masks, but then they remask some of them. So they predict all the mask tokens, but they only keep a subset of those. And so they do some number of steps during sampling, and I think they probably have some examples maybe later on in the paper. I believe this paper had some decent appendices, but I could be imagining it. Okay, we'll talk about some of the other stuff there. Okay, but I think enough talk. Let's try this. Okay, so we're going to do some sampling from a model that's been trained in this way, just to get a kind of more intuitive feel for what's going on. So we're loading a model, and I'll talk about how I train this in a sec. It's not a well-trained model, but it is a masked language model like BERT, except that it's been trained with variable mask ratios. So if I take a prompt, user, what is the best programming language, plus a separator, assistant, colon, and I encode that into token space, right? And I add my start of sequence and so on, and I add a bunch of mask tokens, right? So in this case, 12 mask tokens. If I feed this through the model, and then I decode the results, here's my input. What is the best programming language? Assistant colon. And then I've got Python, Python, comma, 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 is Python, full stop, full stop. Right, so I've got a prediction. It's not a very readable prediction. But it's kind of tough because the model's having to like balance, it's predicting just the most likely token or distribution over tokens for every position, and it's not really given, it's just given a sequence of masks, right? So it's a very tricky problem. You probably want to hedge your bets and say, okay, well, probably some of the parts of a response like that are commas, right? And towards the end, probably they're full stops, right? And somewhere in there is going to be the name of a programming language, and maybe Python is going to be one of the more likely ones. And so that's all it's able to do in that single pass is kind of hedge its bets and guess. And maybe like you can imagine a larger network, this one's only a few 100 million parameters, but maybe a few 100 billion parameters, it would be smart enough to be like, by some intermediate layer, certain positions have kind of like claimed certain words. This is probably going to eventually say Python, so the next one probably eventually will say is, and the other ones are able to attend to those. But for the small model, it's a really hard task. Okay, so why don't we throw away this idea of predicting in one shot and do a little loop. So here again, same setup, what is the best programming language, plus a bunch of mask tokens. But now we're going to go through in a loop 32 times. We're going to get the outputs of the model, and then we're going to say, okay, where is the like maximally confident prediction? And so we could print that here if we said so just going to try and print out. Okay, so we're saying the one that it's most confident about is that at the end there's going to be a full stop. And then at position 15, there's going to be the word is, and 18 is going to be programming, and 19 is going to be language. So you can see, oh, we're starting to see this iterative thing here. Once position 18 is programming, then position 19 is probably language, and then probably before that is best, right? And then probably before that is the. And so when we're looking at just the most likely prediction, we're going to build up this response. Python is the best programming language. It's simple, powerful, and has a wide range of useful features, right? And you can see it's actually filled that in right towards the end of the answer, but the answer starts here. And so, is the best programming language? Question mark A, Python. It's definitely like not perfect, and this starts to give us a feel both for the power of this, right? To reiterate, this is a model that was never trained necessarily in a generative way. It was just trained to predict the correct token whenever it sees a mask. And for most of its training, that was just a flat, I think like 20% masking ratio, right? And then I fine-tuned it for literally like 1 hour on one GPU, maybe 2 hours, and had variable mask ratios. But still, it's only ever seeing a sequence with some tokens masked, and it's predicting those, and yet we were able to turn it into a generator. We're able to turn this unmasking model into something that can generate complete responses by doing this kind of iterative, picking the most likely samples. And we're able to get shockingly coherent, at least for me, for a language model that I've trained or been responsible, been involved in training. This feels like, GPT-2 style. It's able to answer questions level text and somewhat coherent, which is a little shocking, right? And very exciting. But we also start to see immediately some of the flaws. For example, we're choosing how long our answer is going to be right at the start, right? And so unlike an autoregressive model where you could just go token by token until you reach the end of text token, here we suddenly stuck with this like, oh, it needs to constrain its answer to be some certain length, and actually it's going to be trying to guess the answer based on the length, right? Because it can see the sequence and see how many mask tokens it has to work with. So we need to be clever about picking how we do that in advance. Maybe we train it with padding so that it learns to generate lots of padding tokens, but then maybe it always generates lots of padding tokens because they're very likely. Maybe we we figure out ways to delete tokens or insert tokens or try and get around this idea. But yeah, you can see we can at least start to play with these things and hit these limits and start to brainstorm solutions. Okay, so I've just written a function that does exactly what we did, going through this loop. And we can use this to sample a few more completions. Tell me a fun fact about cows. Here's a fun fact about cows. The fact that cows are the most intelligent animals in the world. They can think and make decisions. I love it. I love asking this model about dumb things. You'll see very quickly it starts to get less smart than the programming language example, right? Tell me a joke about lemons. Apostrophe S, a funny joke about lemons. I have a lemonade stand and I'm going to sell lemons. Assistant, that's funny. This is like, a 2-year-old that I know tells this kind of joke. Anyway, but you're welcome to play with this notebook. I will share it. The model itself is up on Hugging Face. And now let's talk briefly about how it was trained, and then let's start to brainstorm ways that we could make this even better. So the training, and I'll also share a version of this, this is just very much like first pass experiment, nothing optimized, nothing too fancy. But we're going to load the model, ModernBERT large, and if you're interested, you should definitely read the paper where my colleagues and friends over at Lighton and other organizations who sort of collaborated on that model documented what they did. This has been trained to predict the masked tokens. It's a masked language model, a kind that's been around for a while. So we can just load this up with the existing Hugging Face infrastructure, and we can load the tokenizer. Then for the data set, I used this one from Allen AI. This is a mixture of many different data sets that they used for their supervised fine-tuning of the Tulu series of models. So it's a fantastic data set. I think something like, nearly 900,000 examples. And so we're going to load up that data set and check it out. And then we're going to sample just the first 512 tokens, clip it if it's longer. We're going to put this very simple formatting, right? User colon, the user piece, separator, assistant colon, the assistant piece, right? So you could imagine doing much better, sort of more traditional chat model formatting. This is just the simplest I could come up with. And then for the assistant part only, right? So we're jumping straight to like the large language model, the sort of supervised fine-tuning part of this. For the assistant part, we're going to apply some masking, right? Either a random amount between full masking, half masking, or no masking. That's going to be dependent on just picking a random mask ratio, right, between the min and the max, and in this case I think I set that to between 15% and 99%. You could tweak this. And so then we're going to mask out that mask ratio of tokens, and I'll talk a little bit about the nuance there. And that's going to give us our data set that looks something like this, right? So we've got a user, here's the question, and then we've got assistant somewhere, sorry, this text, here we go, assistant, mask, 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 problem, mask, 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 right? So this is a fairly high ratio result, but you can see there's still some unmasked tokens in there, but this is on the higher end of masking ratios. And then we've got the labels, so for every mask token, this is the token that should fit in that place. Definitely not the best way to visualize this. We could come up with much more like colorful and useful visualizations. But the core idea is that we've got this training data now where we have some text, a bunch of tokens are masked out, and that's a variable amount, right, between like 15% and 99% of the assistant part masked out. And so then our training loop is going to just be a loop through that data for some number of epochs. We're going to get a batch, we're going to feed it through the model, and we're going to use the standard like out-of-the-box Hugging Face masked language model loss, and then update the parameters accordingly, right? So this is like just continuing the training just like you would a BERT model, except that now our data set doesn't have like a uniform 20% masking ratio. Instead, it's a user question and then a response that's between 10% and 99% masked or whatever. Okay, and so the actual training is very similar, except that I have a validation set so that we can track some stats. We're running through some number of, I think I just did a single epoch, some number of steps, and keeping track of the validation loss, the validation accuracy. And so the validation accuracy at first glance seems pretty high. For the cases where there's super high masking, obviously the accuracy is going to be much lower, but a lot of the cases where there's only, say, 10% of the words, a lot of the times those will be filler words and fairly obvious. But to make it more interesting and clear how that's going, I've actually split this up into buckets. So for the 0 to 25% mask ratio, you can see the accuracy is like 95, 96%. And so it's shockingly good at predicting the ofs, ands, commas, second halves of words, etc., the like low masking ratio pieces. For 25 to 50%, it's still 89.9% accurate. For the 50 to 75%, that's down to 60 something percent. And then for the 75 to 99% masking ratio, it's only 10% accurate. So depending on how completely we've corrupted our data, the model is more or less accurate at predicting what should go in those places. And that makes a lot of intuitive sense, but we should still probably explore, just like in the diffusion literature, instead of that picking a uniform thing, maybe we should spend more time at higher or lower mask ratios. Maybe that should be on a schedule, right? So you have some sort of warm-up starting at the masking ratio that it was trained with. Yeah, definitely we could experiment with all of the training. Everything here was like the first attempt, the first learning rate, the first batch size, etc., that worked on that GPU, in this case an A100. So all of this is definitely like to be experimented with. Other parts should be scale the loss. So remember we said that when you have this kind of masked language model training, you have some number of tokens with the mask and they get the loss applied, but the rest of the tokens don't get any signal. And so if you're having different amounts of masked tokens, right, like you can imagine there's different amounts of signal for a given batch. It could have particularly few masks or many masks. And so open question for me is whether or not we should be scaling the loss according to what percentage or how many of the tokens in the batch are masked. Yeah, can we use larger batches? Keeping a fixed batch for eval, I think I already did that. Full dataset run already did that. But you can see I'm just keeping like to-dos for myself. And then the model gets saved and uploaded to the hub. And we can plot the loss, and you'll see the training loss is extremely noisy. Now, if you're used to normal language model training with a nice cross-entropy signal that's the same amount of signal for every batch, etc., you might think this is an extremely noisy and ridiculous loss curve. If you're used to diffusion model training, you might realize this is actually more par for the course, because remember, we're degrading the inputs by a different ratio, right? So we could have a batch that's like 2 or 3 of the batch are 10% mask ratio, and then one is 30% mask ratio, and the accuracy is very high and the loss is very low. We could have another batch that's mostly 90+% masked, and then the loss is very high. And so when I take a fixed validation set with a fixed mask ratio across it, that gives us a slightly smoother signal, but even here very very noisy, just because everything's small and rough and quick and dirty. So we could definitely use larger batch size or gradient accumulation to get effective larger batch size. Get a larger validation set to get a cleaner signal of the loss over time, and likewise the accuracy. But yeah, you can see the model is learning. Like I said, I put it up on Hugging Face, and I'll share this in the links. And so I guess let's talk next steps. So one, this is a pretty small model still by modern LLM standards, so I think an interesting direction is going to be to try and experiment with hypothetically larger versions of this model, which may or may not be available at some point soon. Another is to experiment with every aspect of the training, right? Trying different data sets, maybe training on generic data first, so spending longer training with different mask ratios on general internet text before switching to the instruction tuning data. The sampling, you'll notice here the sampling notebook that I shared, this is completely deterministic. We're always just taking the max probability, max location, like the most confident prediction of the model, and keeping that. You can instead imagine keeping the 5 most likely tokens each time, right? So we could change our one here. In fact, let's try this. Let's go for iron range answer length over 2. Or let's just do this. And so we're going to go through all of these, but if I is a multiple of 2, we're going to get the model predictions. Otherwise, we'll keep the previous model predictions. And so in practice, this is going to mean we're picking 2 tokens for each forward pass of the model, rather than having to do a single forward pass of the model every single time. And so here we get an answer. There but there's no space, is no best programming language. There are many programming languages. There are popular programming languages like Java, Python, PHP, Ruby, JavaScript, etc. Okay, so it's given us a good attempt at an answer, and now it's different to the one token at a time case. And you can experiment and say, okay, maybe we only do the model prediction every 4 tokens, right? So now it's faster, but maybe it's less good. So yeah, definitely experimenting with different sampling methodologies, using a temperature to tweak the logits and then sample from that distribution rather than always taking the most confident. Definitely a fun thing to try. Applying some remasking, definitely a fun thing to try. I also promised to explain there was some nuance in the masking, and so in BERT style training what actually happens is we don't just feed in a mask token. We pick some percentage of the original tokens to be tweaked, but some of the time we also change the word to a random word from the vocab, right? So this could even say like, you know, bird, or you know, Java, whatever, like random sample from the vocab, and then you get a loss on the token to say, can you correct for this mistake, right? And so I think the ratio that's been used pretty much forever is something like, of the ones to which you're going to be applying a loss and applying some corruption, right? So let's find our data preparation here. We are going to set 80% of them to be the mask token, and we're going to try and predict the correct token. We're going to set 10%, so between 0.8 and 0.9 here in this random generator, to a random token from the vocabulary, and then we're going to leave 10% unchanged. And so this actually gets us like a step towards something that is actually exciting about diffusion models, which this like vanilla masking approach misses, which is that potentially once we've fed through and predict for the masks, if we feed it through again and see that the model actually thinks this particular token that it predicted in the first pass through, we kept it, right? We kept it because it looked likely, but given the other tokens that we kept, it now looks unlikely, right? This training, this noisy training where we're saying 10% of the time, instead of putting a mask, we'll put a random token and we'll have the model predict the correct token. We could potentially be able to leverage that signal to update this token. To say cats appear, right? Or some other like more plausible token. And that gets closer to the ideal of like a diffusion model for language. They are able to like iteratively refine their predictions for every location, right? So you look at the initial predictions and it's generally terrible across the whole image, and then over time, interacting with other parts, it sort of gradually resolves into a reasonable image. And with this sort of vanilla, like naive first attempt at masked diffusion language modeling, once you go from a mask to a token, that's often treated as fixed. But ideally, we'd be able to like repair any bad predictions from earlier in the process over multiple steps. And so that's where this like training on random tokens and replacing them versus training just on mask tokens only seems like a really good idea, and I think is worth exploring further. And for inspiration, the Paella paper did something like this, and if you look at it and then look at the other literature around that in the diffusion for image space, you'll see that they had exactly this. Instead of using mask tokens like some of the other discrete diffusion image model stuff, they would take in a noise mask and apply noisy tokens and try and predict the correct tokens, as opposed to the random tokens that were fed in. So I think definitely that's an interesting area to explore, and potentially fine-tune the model on only random tokens with no masking, and do this kind of like progressive, replacing the random ones with better predictions, and then replacing those with even better predictions. This progressive decrappification, progressive improvement, whatever you want to call the like core idea behind things like diffusion, flow matching, and so on. Okay, so I think that's a pretty good overview of where I'm at with these experiments and the ideas that I'd like to pursue. Hopefully that's given you lots of ideas for things that you can try. Like I said, I'll share the sampling notebook and the training notebook and the links to the data sets and papers and so on. But yeah, I think there's lots and lots of space to iterate and explore, and also you can start to see the one more thing. So you can start to see the limitations, especially with the fixed length response and so on. And so in a follow-up video, another thing I'd like to explore, and another thing you could potentially start experimenting with if you're interested in following along, is how do you deal with like variable length generation, right? So you can see in the large language diffusion models paper, they do this in blocks, and so they progressively unmask a block right? So they start with full masking, and then they keep half of the predictions, and then they keep full of the predictions. This is very simplified. And then they move on to the next block, and so they add more masks, and they unmask that way. So you get this kind of like autoregressive nature, and you can imagine adding more blocks until you get to one with a stop token or an end of sequence token or whatever you've trained in as the end of a response. But that's still not ideal. So then there's also esoteric. I think this is the one that has things like instead of training on mask tokens, training on insertions and deletions. Oh, sorry, no, this is the wrong paper. Okay, we'll leave that for a future video, but figuring out ways to like expand, right, insert or delete tokens, replace tokens, rather than just having to guess how many mask tokens you need to start with. Yeah, lots and lots and lots of space in this general idea of moving away from pure autoregressive sampling and into a much more rich and interesting parallel but progressive refinement type approach for language. So I hope you found this interesting. Do leave lots of comments if you're curious, if there's questions that you'd like to see addressed. I'm going to keep playing with this. I'll keep you updated, but I thought it was worth making an initial video now so that others can get involved, and then as we go we can see how much better we can get this and how many fun facts about cows and other things we can learn from these models. Thank you so much for watching.